Or whether it has a bad word with it, I think, I don't know. It's I was gonna get that with it. Okay. Okay, so compound, right? Two types of compounds, molecular, ionic. Okay. Molecular, actually, it's a good point up there. We can, a synonym for molecular is covalent compound. There's a reason for that. I think I'll have enough room down here. Can't remember again, when you clear back in Unit 1 when we took matter and kind of says pure substance or mixture and all that. Can't remember if we got down to the nitty gritty that compare and contrast. But, so synonym for molecular compound is covalent. So you'll see me kind of go back and forth between those two words. This repeating unit is a molecule, and this repeating unit is a formula unit. Yeah, I think I did this because the abbreviation for formula unit is FU. I'm sorry, but it really is. It totally is. Compare and contrast. Metals bonded with nonmetals produced ionic compounds. So under ionic compounds, I would put M for metal. This dash is my bonded to nonmetal. Okay? That's an ionic compound. In general then, over here, for a molecular compound, we have all nonmetals. So to me, I'm a visual person, so I put non-M for my nonmetal atom, joined to another nonmetal atom, non-N. So we have to remember, like, I don't know what's a metal and what's not a metal. Well, who should remember? So the periodic table, we can remember we can chunk it up, and this jag actually separates the metals. So these are still metals, and this little thing up here is the nonmetals. And we said along the jag are kind of a handful of what we call metalloids. So methane is an example of a molecular or covalent compound. I said nonmetal joined to nonmetal gives you a covalent compound. So over here, I have to, under molecular or covalent compounds, I have to say H, as in the element hydrogen, is equal to a nonmetal. Okay, so if we're given the formula CH4, you're like carbon. Let me find the periodic table. Nonmetal, right? Carbon, it's in the little jag, or it's in the little triangle. Nonmetal, hydrogen, nonmetal, nonmetal, nonmetal. It makes it a molecular compound instead of ionic compound. Water. Hydrogen is a nonmetal for all intents and purposes, usually. Oxygen, we find in the periodic table, also a nonmetal. Nonmetal, nonmetal, molecular compound. Let's see, I bet the other one's a molecular compound too. Ammonia, nitrogen, find it in the little triangle stuff, nonmetal. Hydrogen, nonmetal, nitrogen, nonmetal, NH3 must be two nonmetals. It's a molecular compound. So this is trying to kind of emphasize with a molecular compound, such as up here, the repeating unit is a nice little, cute little awesome molecule. The cool thing about molecules, it's kind of like a magician who kind of has his or her assistant hovering in thin air. One of the things they always do is they hover their assistant, which I have no idea how magicians do their thing. But then they'll take their magical wand and they'll kind of go, see? And they'll take their magical wand and go all the way around the person. So that's a molecule. It's just like all by itself. Okay, we're going to compare that to a repeating unit of an ionic compound. Molecules are all by themselves. Okay, this video, I can play it, but all it does is kind of rotate it, kind of reminds me of the magician who says, see, it's not connected to anything. Ammonia. If we compare that now to the compound sodium chloride. So, if you find a metal, so this is what you're looking for. In music sometimes, I might have used this before, we use like little eyeglasses to make sure, like if we're rehearsing music, that means watch the conductor. So in this case, it means look for the metal. If you have a metal in the formula of your compound, you're like, dude, gotta be an ionic compound. So go ahead and put your JAG, NaCl. So if you find Na on the periodic table, you're like, metal. Cl, non-metal. Metal and non-metal equals an ionic compound. A metal anywhere in your formula, ionic compound in general. So we're going to be kind of comparing what's different about sodium chloride versus what? An ionic compound versus a molecular compound. And I'm going to show you these videos again, even though we've seen them before, because they emphasize what happens in an ionic compound is you've got to get an ion to be formed. If anybody says, hey, I've got an ion here, all they're saying is the opposite of an ion is a neutral atom. They're saying you don't have a neutral atom, you have something that's charged. So if it was neutral, it had the same number of electrons, the same number of protons. If it's an ion, not so much, okay? So an electron is transferred, we're going to see it's given up, an electron is given up by the metal and taken in by the non-metal. So let's check out this. Okay. So again, well, this looks a little backwards to me because the bigger ones, the purple looks bigger, and actually the bigger ones should be the negative charged anions. So if we compare sodium chloride with H2O, an H2O molecule is going to have an H2O molecule. H2O, it's got 3 atoms that are stuck together. I don't have a video about it, but it looks like this, where we'll talk more about why it's like this, but it actually has this, what we call a bent shape, where it has a central oxygen atom and 2 hydrogen atoms that are kind of squished down like that, okay? So my thing about it is there's no other, well, there will be what we call hydrogen bonds or intermolecular bonds, but there's no other chemical bonds connecting them. Now, if I put back my NaCl, usually, for whatever reason, when I show a bond between a cation, I'll put a plus here for the sodium, and a chlorine, and an anion, I'll put a negative here for the chlorine. And remember how it got that way? It took an electron. Electron was transferred from the sodium to the chlorine to make that positively charged and that negatively charged. What I started to say is I usually put a dash there. For that sort of bond is an ionic bond. And we'll be talking more about this on Wednesday and maybe Lab Friday or Lab Thursday. Ionic bond, electron was transferred. And these guys are actually covalent bonds, and electrons were shared. Okay, so this is just kind of comparing and contrast. So covalent bonds actually, I'm going to go back over here for my covalent compound. I'm going to add something to it. For covalent compounds, you need to have all the bonds joining the atoms, all chemical bonds, I'll put chem bonds, equals covalent bonds. And what are covalent bonds? Covalent bonds are where electrons are shared. Ionic bonds, electrons are transferred, and I'll go ahead and under the ionic compound, I'm going to say at least one ionic bond. And this probably is somewhere else in my notes, I think, but if it has, it's contaminated. At least one ionic bond, it contaminates it and makes it an ionic compound. What's an ionic bond? We must have had an electron transferred, creating a positively charged species called a cation, and a negatively charged thing called an anion. See, I guess I had it. Ionic bond, compound that contains, ionic compound. Compound that contains at least one ionic bond. Covalent compound, only covalent bonds. Seems like I already said all that. All right. just gonna 5 minutes. This is a cool concept. This almost gives the atoms personality. So in physical science, a lot of times we will draw on the Greek alphabet. So that thing looks like an X. It's actually the Greek letter chi. C-H-I, chi. And it refers to an atom's electronegativity. An atom's electronegativity is the ability for, or the want an atom wants to hold on to its own electrons, but also steal electrons from somebody else. Okay? The ability of an atom to attract electrons to itself, whether it's its own or somebody else's. The way this works is metals are like, electrons, I can do without a few. So find the Jag, and all these metals have low chi, low electronegativity values. Okay, non-metals, so they already came up. The non-metals have high chi, high electronegativity values. And that's actually kind of consistent with what we saw with sodium chloride. The sodium's a metal. What did it want to do? You can have that electron, right? Chlorine, what did it want to do? Yeah, give me the electron. Okay. So we see this trend if we take the A's, which we have 2 columns here and 6 columns here, so take those guys out. Squish them together, we have this trend. So electronegativity increases from left to right, and electronegativity increases from the bottom up. Okay, so you're going to have this sort of thing, increasing electronegativities. Which, this idea of electronegativity, we're going to talk about it in terms of electrons being transferred or shared, but it's a player in chemistry a lot, electronegativity. This is a look at electronegativity values. The higher the bar, the higher the electronegativity. Notice it's got actually the B elements in here too. We kind of have some of the transition elements do some funky things with regard to electronegativities. But you can see high bars over here for the metals. No, I'm sorry, high bars over here for the non-metals, sorry about that, and low bars over here for the metals. Low electronegativities, have my electron. High electronegativities, gave you electrons. Okay. Linus Pauling is a Nobel Prize in Chemistry winner, I believe, for his work in this area. So that was a bar chart. This actually is the same. These are values. These are actually electronegativity values. You'll hear me call them Pauling values or Linus Pauling. So Pauling values, electronegativity values, they mean the same thing. Again, where are they high? Over here with non-metals, low for the metals. So here's the deal. If I were to put up a little triangle here, and I go delta T, you'd say differences in temperature, right? If I put up a delta chi, hopefully you would say that's differences in electronegativities. So we actually do a lot of these easy subtraction problems. Delta chi's come in, like if you have atom A joined to atom B, okay, and you want to evaluate what's going on with regard to their electronegativity difference, all you got to do is, and I don't have a formula for this in my notes. Delta chi is equal to, I usually do the absolute value of the electronegativity of A minus the electronegativity of B. The absolute value of. That's the electronegativity difference. Well, and it's like if you're playing tug of war and the other team isn't like really pulling very hard, you're going to get the rope, right? Electron's going to be transferred. So large differences in electronegativity differences, electrons transferred, bonds ionic. Okay? Where life gets a little interesting is if you have 2 atoms that are like, yeah, I want my electron. I do too. Okay? So there's a tug of war, so electron won't be transferred. It's going to be actually shared between them. Shared equally? Not necessarily, but no one's going to win in that tug of war. Okay?
And if like the bonds between like the same elements,
Bonds between the same elements, standoff. That's what we call perfectly covalent. Yep, the delta chi is 0. But I think we bumped up against our time, guys. So more on that on Wednesday for most of us.